awesome.
You want to know something absolutely mind-bending? Right now, as you're sitting there, comfortable, maybe sipping your coffee, scrolling through your day, there are machines we built with human hands flying through the void of space. They're out there, right now, traveling at speeds that would make a fighter jet look like it's standing still. And they're headed to worlds so distant, so alien, that the very concept of getting there becomes almost philosophical. But here's the thing. We did it. We launched them. We calculated the trajectories. We figured out the math. And most remarkably, we actually got there. So let's talk about travel time. Not the kind where you're stuck in traffic, wondering if you should have taken the highway. We're talking about the kind of travel that redefines what patience means. The kind that makes a cross-country road trip look like a walk to your mailbox. Let's start with our cosmic neighborhood. Let's start with the numbers that'll make you rethink everything you thought you knew about distance. Picture this. You're standing on Earth. You look up. You see the moon. It's right there. Close enough that you can see its features with your naked eye. That pale disk hanging in our sky has been humanity's companion since before we were human. Every culture, every civilization, every person who's ever lived has looked up and seen that same moon. The moon is, on average, about 238,855 miles away from Earth. In cosmic terms, that's nothing. That's right next door. That's your neighbor's house. The Apollo astronauts who went there in the late 1960s and early 1970s made the journey in about 3 days. 3 days. Think about that. 3 days to leave Earth and set foot on another world. But here's where it gets interesting. The moon isn't a planet. It's our natural satellite, a chunk of cosmic real estate that's been orbiting Earth for over 4 billion years. So when we talk about getting to the planets, we're talking about something entirely different. We're talking about crossing distances that make the moon seem like it's practically touching us. Let's go to our first real planetary neighbor. Let's go to Venus. Venus, the morning star, the evening star, that brilliant point of light that outshines everything in the sky except the sun and the moon. Ancient cultures worshipped it. They wrote poems about it. They built temples to track its movements across the heavens. And for good reason. Venus is breathtaking. When it's visible, it's impossible to miss. It hangs there in the twilight, blazing like a cosmic beacon, beautiful and enigmatic. But Venus is also a nightmare world. And getting there, that's where the story gets really interesting. Venus orbits the Sun at an average distance of about 67 million miles. Earth orbits at about 93 million miles. So you might think, okay, simple math, Venus is about 26 million miles away, right? Wrong. Dead wrong. Because nothing in space is simple. Nothing stays still. Earth is moving, Venus is moving. They're both going around the Sun, but at different speeds, in slightly different orbital paths. Sometimes Venus is on the opposite side of the Sun from us. In that configuration, it's about 162 million miles away. Sometimes, when the orbital mechanics align just right, Venus comes to what we call inferior conjunction. That's when it passes between Earth and the Sun. In that configuration, Venus can be as close as 24 million miles from Earth. 24 million miles. That's the closest any planet gets to us. Venus is our nearest planetary neighbor, not Mars, despite all the hype. So how long does it take to get there? That depends on how you're traveling and when you're launching. The first successful mission to Venus was Mariner 2 back in 1962.
It took about 109 days. That's roughly 3.5 months. Mariner 2 traveled along what we call a Hohmann transfer orbit. It's the most fuel-efficient path between two planets. You don't just aim at where the planet is, you aim at where it's going to be. You fire your rockets at just the right moment, and you let gravity do most of the work. Later missions varied. The Soviet Venera program, which successfully landed multiple probes on Venus's hellish surface, had transit times ranging from about 95 to 120 days, depending on the launch window and trajectory chosen. NASA's Magellan spacecraft, launched in 1989, took 15 months to reach Venus. But that's because it used a different, more energy-efficient trajectory that involved multiple loops. But here's the crucial point. We're talking about months, plural. To reach our closest planetary neighbor, you're looking at a minimum of about 3 months if everything aligns perfectly. And that's using chemical rockets, the kind of propulsion system we've been using since the dawn of the space age. Now let's talk about why nobody talks about going to Venus. Because it's literally hell. The surface temperature is hot enough to melt lead, hovering around 900 degrees Fahrenheit. The atmospheric pressure is 90 times what we experience at sea level on Earth. That's like being 3,000 feet underwater in Earth's oceans. The atmosphere is almost entirely carbon dioxide, laced with clouds of sulfuric acid. It rains sulfuric acid on Venus. The wind howls at hundreds of miles per hour in the upper atmosphere. The surface is dotted with volcanic features, and we think some of them might still be active. And yet, we went there multiple times. The Soviets managed to land probes that survived for a few hours before the heat and pressure crushed them into oblivion. They sent back pictures, grainy, precious images of a landscape so hostile, so utterly alien that it redefines what we mean by uninhabitable. So Venus is off the table for human exploration anytime soon. Which brings us to the planet that everyone actually wants to visit, the planet that has captured our imagination for over a century, the planet that, despite being farther away, seems somehow more welcoming.
Mars, the red planet, fourth rock from the sun, the world that ancient Romans named after their god of war because of its blood-red color in Earth's night sky. The planet that Giovanni Schiaparelli looked at through his telescope in 1877 and thought he saw canali, which got mistranslated into English as canals, which led Percival Lowell and countless others to spend decades searching for signs of Martian civilization. There are no canals on Mars. There are no Martians building vast irrigation networks. But there is a world, a real, tangible world with mountains taller than Everest, canyons that would swallow the Grand Canyon, polar ice caps that grow and shrink with the seasons, and dust storms that can engulf the entire planet. Mars orbits the Sun at an average distance of about 142 million miles. Earth orbits at 93 million miles. So Mars is farther from the Sun than we are. But just like with Venus, the distance between Earth and Mars changes constantly. When Earth and Mars are on opposite sides of the Sun, they can be as far apart as 249 million miles. When they line up on the same side of the Sun, at what we call opposition, they can be as close as 34 million miles. 34 million miles, that's the minimum. That's the cosmic sweet spot we wait for. And we do wait, because launch windows to Mars only come around every 26 months. That's how long it takes for Earth and Mars to align in their orbits in a way that makes sense for launching a spacecraft. Miss your window? You're waiting over 2 years for the next one. So how long does it take to get to Mars? The answer is, it depends. But let's look at the track record. Mariner 4, the first spacecraft to successfully fly by Mars, launched in 1964 and took 228 days to get there. That's about 7.5 months. The Viking orbiters and landers in 1976 took a little under a year. More recent missions like Mars Reconnaissance Orbiter took 7 months. The Perseverance rover, which launched in 2020 and landed in 2021, took about 7 months. You see the pattern? 7 months. That's the sweet spot. That's how long it takes using current chemical rocket technology on a Hohmann transfer orbit when you time it right. 7 months of coasting through the void. 7 months of waiting. 7 months during which everything has to work perfectly because there are no mechanics in space, no AAA to call if your engine fails. But here's what blows my mind. We've gotten good at this. Really good. We've sent dozens of missions to Mars. Orbiters, landers, rovers. We've landed car-sized robots on Mars using rocket-powered sky cranes. We've driven rovers across Martian soil for years, even decades. Opportunity, one of the Mars rovers, was designed to last 90 days. It lasted 15 years. 15 years! That's not just engineering, that's artistry. And people want to go there. Real people. You, me, your neighbor. We want to send humans to Mars. And when we do, they'll face that same 7-month journey. 7 months in a cramped spacecraft. 7 months of cosmic radiation. 7 months of wondering if the life support systems will hold up. 7 months of being farther from home than any human has ever been. But we'll do it, I have no doubt, because that's what we do. We explore, we push boundaries. We look at a distant red dot in the sky and say, I want to go there. Now, Mars is special because it's the only planet beyond Earth where we seriously talk about sending humans. But the solar system doesn't end at Mars, not by a long shot. Beyond Mars lies a realm that redefines what we mean by distance. Beyond Mars, the travel times stop being measured in months and start being measured in years.
Let's talk about Jupiter. Jupiter, the king of planets, the giant, the behemoth, a world so massive that you could fit 1,300 Earths inside it. A world with a great red spot that's a storm bigger than Earth, a storm that's been raging for at least 400 years. A world with 95 known moons, some of which might harbor oceans beneath their icy crusts. Jupiter orbits the Sun at an average distance of 484 million miles. That's 5.2 times farther from the Sun than Earth. And the distance between Earth and Jupiter? It varies wildly. At its closest approach, Jupiter is about 365 million miles from Earth. At its farthest, it's about 601 million miles away. So how long does it take to get there? Let's look at what we've actually done. Pioneer 10, launched in 1972, took 21 months to reach Jupiter. That's a year and 9 months. Pioneer 11, launched in 1973, took a similar amount of time. The Voyager spacecraft, those legendary robots that are now in interstellar space, took a bit less time. Voyager 1 reached Jupiter in about 18 months. Voyager 2 took about 20 months. But here's where it gets interesting. These early missions were doing flybys. They weren't stopping. They were slingshotting past Jupiter, using its gravity to boost their speed and send them on to Saturn and beyond. When you want to actually stop at Jupiter, to go into orbit around it, you need to slow down. And slowing down takes fuel and time. The Galileo spacecraft, which launched in 1989, took 6 years to reach Jupiter. 6 years! But that's because it took a scenic route, flying past Venus once and Earth twice to pick up gravitational assists. Once it got to Jupiter in 1995, it went into orbit and spent 8 years studying the planet and its moons. It sent a probe diving into Jupiter's atmosphere. It discovered evidence of subsurface oceans on Europa. It revolutionized our understanding of the Jovian system.
Juno, the most recent mission to Jupiter, launched in 2011 and took 5 years to get there, arriving in 2016. It also used gravitational assists to make the journey more fuel efficient. So the answer is, if you're just flying past Jupiter, you're looking at 18 to 24 months. If you want to go into orbit with current technology, you're looking at anywhere from 2 to 6 years, depending on your trajectory and how many gravitational assists you can line up. 2 to 6 years. Let that sink in. That's longer than a college degree. That's longer than most presidencies. That's a significant chunk of a human lifetime. And that's just to get to Jupiter. But here's the thing about Jupiter. It's worth it. Jupiter is a laboratory for understanding planetary formation. It's a window into the early solar system. Its moons, Europa, Ganymede, Callisto, Io, these aren't just rocks. They're worlds unto themselves. Europa probably has twice as much water as all of Earth's oceans combined, locked beneath an icy shell. If there's life in our solar system beyond Earth, Europa is one of the top candidates, and we're going back. NASA's Europa Clipper mission launched in 2024 and will reach Jupiter in 2030. That's 6 years of travel. 6 years to reach a moon that might harbor life. 6 years that will feel like an eternity to the scientists and engineers who built the spacecraft, but will pass in a blink on cosmic timescales.
Now, if Jupiter seems far, hold on to something, because we're about to talk about Saturn. Saturn, the ringed planet, the jewel of the solar system, the planet that, when you see it through a telescope for the first time, makes you gasp. Because those rings are real. They're actually there. Billions of chunks of ice and rock, each one orbiting Saturn independently, creating a structure so thin relative to its width that if you made a scale model using paper for the rings, the paper would be thousands of times too thick. Saturn orbits the Sun at an average distance of 886 million miles. That's 9.5 times farther from the Sun than Earth. The distance between Earth and Saturn varies from about 746 million miles at closest approach to about 1.03 billion miles at its farthest. 1 billion miles. We've crossed into the billions now. And the travel times? They're measured in years. Multiple years. Pioneer 11, the first spacecraft to reach Saturn, took 6.5 years to get there after launching in 1973. Voyager 1 took 3 years and 2 months. Voyager 2 took 4 years. But again, these were flybys. They were using Jupiter's gravity to slingshot themselves toward Saturn at high speeds. Cassini, the mission that orbited Saturn from 2004 to 2017 and gave us the most detailed views of Saturn we've ever had, took nearly 7 years to reach Saturn after launching in 1997. 7 years. Think about where you were 7 years ago. Think about how much has changed in your life since then. That's how long it took Cassini to cross the gulf between Earth and Saturn. But once it got there, Cassini spent 13 years orbiting Saturn. 13 years studying the rings, the atmosphere, the magnetosphere. It carried a probe called Huygens that landed on Titan, Saturn's largest moon, and sent back the first images from the surface of a moon in the outer solar system. It discovered geysers of water erupting from Enceladus, another moon, suggesting yet another subsurface ocean that might harbor life. Cassini's mission ended in 2017, when, low on fuel and unable to continue operating safely, it was deliberately crashed into Saturn's atmosphere. It burned up like a meteor, a fitting end for a spacecraft that had given us so much. And in those final moments, even as it was being torn apart by Saturn's atmosphere, it was still sending back data. 7 years to get there, 13 years of operations,
20 years total. That's a career. That's someone's entire professional life from the launch to the end. That's dedication. That's commitment. That's what it takes to explore the outer solar system. And we're still not done. Beyond Saturn lie worlds even more distant. Worlds where the sun is just another bright star. Worlds where the very concept of a mission takes on almost mythical proportions.
Let's talk about Uranus. Uranus is known as the ice giant, the planet that orbits on its side, its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Imagine if Earth's North Pole pointed almost directly at the sun during summer and away from the sun during winter. That's Uranus, and nobody knows why. The leading theory is that early in the solar system's history, something massive, maybe another planet-sized object, collided with Uranus and knocked it over. And it's been rolling around the sun like a ball ever since. Uranus orbits at an average distance of 1.8 billion miles from the sun. That's 19 times farther than Earth. The distance between Earth and Uranus varies from about 1.6 billion miles to about 1.98 billion miles. 2 billion miles. We are deep in the outer solar system now. And only one spacecraft has ever visited Uranus, Voyager 2. Voyager 2 launched in 1977 and reached Uranus in 1986. That's 8.5 years of flight time. 8.5 years to reach a world so distant that even light, traveling at 186,000 miles per second, takes about 2 hours and 40 minutes to get there from the sun. Think about that. When you look at Uranus through a telescope, you're not seeing it as it is now. You're seeing it as it was nearly 3 hours ago. The light you're seeing left Uranus when you were eating breakfast, or sleeping, or going about your day, and it's been traveling through space ever since. Voyager 2 spent just a few hours in the Uranus system during its flyby. A few precious hours after 8.5 years of travel. It discovered new moons. It studied the planet's atmosphere and magnetic field. It took images that remain the best we have of Uranus to this day. And here's the thing. We haven't been back. Not once. Voyager 2 flew past Uranus in 1986, and in the nearly 4 decades since, no other spacecraft has visited. It's too far. The mission times are too long. The budgets are too big. The challenges are too great. But that might be changing. NASA is considering a mission to Uranus, possibly launching in the 2030s. With modern technology and clever use of gravitational assists, such a mission might be able to reach Uranus in as little as 12 to 13 years. 12 to 13 years. A newborn baby when the mission launches would be a teenager when it arrives. That's the scale we're talking about. And yet, Uranus isn't even the most distant planet. That honor belongs to the king of the deep freeze, the lord of the outer darkness, the planet at the edge of the classical solar system.
Neptune, the blue planet, the windiest planet in the solar system, with winds that can reach 1,200 miles per hour. A world with storms and clouds, and a great dark spot reminiscent of Jupiter's great red spot. A world with a large moon, Triton, that orbits backward and probably didn't form around Neptune, but was captured from the Kuiper belt. Neptune orbits at an average distance of 2.8 billion miles from the Sun. That's 30 times farther than Earth. The distance between Earth and Neptune varies from about 2.7 billion miles to about 2.9 billion miles. Nearly 3 billion miles. Light takes more than 4 hours to travel from the Sun to Neptune. When you send a command to a spacecraft at Neptune, you wait 4 hours for the signal to get there, and then you wait another 4 hours to find out if it worked. That's an 8-hour round-trip communication delay. You can't fly a spacecraft at Neptune in real time. You have to program it to operate autonomously, to make its own decisions, because by the time you find out something's wrong, it's too late to fix it. Voyager 2, the only spacecraft to ever visit Neptune, took 12 years to get there. 12 years! It launched in 1977 and arrived at Neptune in 1989. 12 years of flight through the solar system using gravitational assists from Jupiter, Saturn, and Uranus to maintain its speed. When Voyager 2 reached Neptune, it had been in space longer than many of the engineers working on the mission had been in their careers. People had gotten married, had kids, watched those kids grow up, all while Voyager 2 was en route to Neptune. And just like at Uranus, Voyager 2's encounter with Neptune was brief. A few hours of close-up observations during the flyby. A few hours to gather data, take pictures, make measurements. And then it was gone, continuing on its trajectory out of the solar system, leaving Neptune behind in its rearview mirror. We haven't been back to Neptune either. No missions are currently planned, though there are proposals. A mission to Neptune and Triton would take somewhere between 12 and 15 years with current technology, depending on whether you could line up gravitational assists. 12 to 15 years. That's high school and college. That's from childhood to adulthood. That's how long it would take to send a spacecraft to the outermost planet in our solar system. But wait, there's more. Because the solar system doesn't end at Neptune. Beyond Neptune lies a realm of icy bodies, dwarf planets, and ancient remnants from the formation of the solar system. And one of them used to be considered a planet.
Pluto. Oh, Pluto. Pluto, the subject of so much controversy. Pluto, discovered in 1930 and considered the 9th planet until 2006, when the International Astronomical Union redefined what it means to be a planet, and Pluto didn't make the cut. Pluto, now classified as a dwarf planet, but no less interesting for it. Pluto orbits the Sun at an average distance of 3.67 billion miles. That's nearly 40 times farther from the Sun than Earth. But here's the thing about Pluto. Its orbit is highly elliptical. Sometimes it's as close to 2.7 billion miles from the Sun, actually closer than Neptune. Sometimes it's as far as 4.6 billion miles from the Sun, deep in the Kuiper Belt. 4.5 billion miles. That's not a distance the human mind can really grasp. Light takes over 6.5 hours to travel from the Sun to Pluto when Pluto is at its farthest point. Only one spacecraft has ever visited Pluto, New Horizons. New Horizons launched in January 2006, just months before Pluto was demoted from planet status. It was the fastest spacecraft ever launched at the time, reaching a velocity of about 36,000 miles per hour as it left Earth. And even at that speed, even being the fastest thing humanity had ever built, it took 9.5 years to reach Pluto. 9.5 years.
New Horizons launched when YouTube was barely a year old. It reached Pluto after Instagram had been around for 5 years. Think about how much technology changed in that time. Think about how much the world changed. And all the while, New Horizons was speeding through space, covering millions of miles every day, and yet taking nearly a decade to reach its destination. The encounter itself lasted just a few hours, with the closest approach happening on July 14, 2015. A few hours of close-up observations after 9.5 years of flight. New Horizons took images that revealed Pluto to be far more complex and interesting than anyone had imagined. Mountains made of water ice as hard as rock, glaciers of frozen nitrogen, a heart-shaped region that became iconic, a thin atmosphere, multiple moons. And then, New Horizons kept going, deeper into the Kuiper Belt. In 2019, it flew past a small snowman-shaped object called Arrokoth, the most distant object ever visited by a spacecraft at the time. And it's still out there, still functioning, still sending back data, now more than 5 billion miles from Earth. 5 billion miles. The radio signals from New Horizons take more than 7 hours to reach Earth, traveling at the speed of light. 7 hours. You could watch an entire Lord of the Rings movie trilogy, and the signal still wouldn't have made it back to Earth. So, let's recap. Let's put this all in perspective, because when you line up these numbers, when you really think about what they mean, it's staggering.
Mercury, the closest planet to the Sun, varies in distance from us between 48 million and 138 million miles, depending on where both planets are in their orbits. The Mariner 10 mission, which flew past Mercury 3 times in 1974 and 1975, took about 5 months to make its first encounter. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, took about 6.5 years to get there, using multiple gravitational assists to make the journey. Bepi-Colombo, a joint European-Japanese mission currently en route to Mercury, will take 7 years to arrive after its 2018 launch. 7 years to reach the closest planet to the Sun. Why? Because Mercury is deep in the Sun's gravity well. You can't just fly there directly. You have to carefully navigate the gravitational landscape, using multiple flybys of Venus and Mercury itself to gradually slow down enough to enter orbit. It's like trying to land on a moving train while riding a bicycle. The physics is mind-bogglingly complex. Venus, our closest planetary neighbor at times, takes about 3 to 4 months to reach on a direct trajectory. Mars takes about 7 months. Jupiter takes 2 to 6 years, depending on whether you're doing a flyby or entering orbit. Saturn takes 3 to 7 years. Uranus takes 8 to 13 years. Neptune takes 12 to 15 years. Pluto takes 9 to 10 years. And those are just travel times using current chemical rocket technology and gravitational assists. If we want to go faster, if we want to reduce these times, we need new technology. We need new propulsion systems. There are concepts. Oh, there are concepts. Ion drives that provide continuous low thrust for years, gradually accelerating to speeds much higher than chemical rockets can achieve. The Dawn mission used ion propulsion to visit both Vesta and Ceres in the asteroid belt, something that would have been impossible with conventional rockets. Nuclear thermal rockets that could potentially cut travel times to Mars in half. Solar sails that use the pressure of sunlight to accelerate, no fuel required. And more speculative ideas like nuclear pulse propulsion,
antimatter drives, even warp drives that bend space-time itself. But for now, for the missions we're flying today and will fly in the next decade or two, we're stuck with chemical rockets and careful orbital mechanics. We're stuck with travel times measured in months and years. We're stuck with the brutal reality that space is big, really big. Douglas Adams had it right when he wrote in The Hitchhiker's Guide to the Galaxy, "Space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts to space." He was talking about interstellar distances, distances to other stars. But even within our own solar system, the numbers are staggering. The average distance from the Sun to Neptune is about 2.8 billion miles. The average distance from the Sun to Pluto is about 3.67 billion miles. But the nearest star beyond the Sun, Proxima Centauri, is about 25 trillion miles away. That's nearly 7,000 times farther than Pluto. With current technology, it would take tens of thousands of years to reach Proxima Centauri. The Voyager spacecraft, which are the most distant human-made objects and are now in interstellar space, are traveling at about 38,000 miles per hour relative to the Sun. At that speed, it would take them about 75,000 years to travel the distance to Proxima Centauri, if they were headed in that direction, which they're not. 75,000 years. That's more time than recorded human history. That's more time than our species has had agriculture. That's how far away the nearest star is. But let's bring this back to our solar system, because here's the beautiful thing. We can reach the planets. With patience, with clever engineering, with careful planning, we can send our robots to every planet in the solar system, and we have. We've sent spacecraft to Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. We've orbited some of them. We've landed on some of them. We've collected samples and brought them back home. And we're planning more missions. NASA's Dragonfly mission will send a nuclear-powered drone to Titan, Saturn's largest moon, arriving in the mid-2030s. It'll fly through Titan's thick atmosphere, hopping from location to location, studying the organic chemistry that's happening on this moon that, in some ways, resembles a frozen version of early Earth. The Europa Clipper mission will conduct dozens of close flybys of Jupiter's moon Europa, looking for the best places to land a future mission that might search for life in Europa's subsurface ocean. China has declared its intention to send missions to Jupiter and Uranus. The European agency is planning JUICE, the Jupiter Icy Moons Explorer, which will study Jupiter's large icy moons. We are living in a golden age of solar system exploration. And yes, the travel times are long. Yes, the challenges are enormous. Yes, it takes years, sometimes a decade or more to get to the outer planets. But we're doing it. We're sending our emissaries to distant worlds, and they're sending back knowledge, insight, and images that take our breath away.
And one day, maybe not in my lifetime, maybe not in yours, but one day, we'll send humans beyond Mars. We'll figure out how to keep people alive and healthy for the multi-year journeys to the outer solar system. We'll develop the life support systems, the radiation shielding, the propulsion technology. We'll build ships that can sustain human life for years in the void. Maybe we'll have bases on the moons of Jupiter or Saturn. Maybe we'll mine the asteroids for resources. Maybe we'll establish colonies on Mars and use it as a stepping stone to the outer solar system. Maybe we'll develop technologies we can't even imagine yet. Technologies that make the journeys faster, safer, easier. Or maybe we won't. Maybe humans will never travel to the outer planets in person. Maybe we'll always explore through our robotic proxies, our spacecraft, our rovers, our orbiters. And you know what? That's okay too. Because the robots we build are extensions of ourselves. There are eyes and ears in places we can't yet go. There are hands touching alien soil. There are presence on distant worlds. Every time a spacecraft reaches a planet, every time it goes into orbit, every time it lands, every time it sends back data, that's a human achievement. That's us reaching out across the void, touching the cosmos, learning, discovering, exploring. The journey times are long, yes, months to the inner planets, years to the outer planets, but every one of those missions is worth it. Every image, every measurement, every discovery adds to our understanding of the solar system, of planetary science, of how worlds form and evolve. And here's something else to consider. While our spacecraft are in transit, they're not just sitting idle. They're making observations. They're collecting data on the solar wind, on cosmic rays, on magnetic fields, on dust particles. The journey itself is part of the mission. Voyager 1 and Voyager 2 are now in interstellar space, beyond the influence of the sun's solar wind, and they're sending back data about what interstellar space is like. That data is invaluable. We've never had measurements from interstellar space before, and those measurements are only possible because Voyager had to spend years traveling through the solar system to get there. The New Horizons spacecraft, after its encounter with Pluto and Arrokoth, continues to send back data about the Kuiper Belt, the distant region of icy bodies beyond Neptune. That data is helping us understand the structure of the outer solar system in ways we never could before. So the travel times, as long as they are part of the story. They're part of what makes space exploration so challenging and so rewarding. If it were easy, if we could just hop on a spacecraft and be at Mars in a few hours or Jupiter in a few days, it wouldn't mean as much. The difficulty, the time, the patience required, that's what makes it an achievement. And let's not forget, in the cosmic scheme of things, even a 15-year journey to Neptune is nothing. The solar system is 4.6 billion years old. The journey of a spacecraft is a blink of an eye in comparison. The planets have been orbiting the sun for billions of years. They'll continue to orbit for billions more. Our spacecraft, our missions, our explorations, they're moments in cosmic time. But they're our moments. They're humanity's moments. They're the times when we reach out and say, we're here, we're curious, we want to know, we want to understand. Every planet has its own story, its own mysteries, its own wonders. Mercury, with its huge iron core and cratered surface, tidally locked in a 3-to-2 resonance with the Sun. Venus, Earth's evil twin, a cautionary tale of runaway greenhouse effect. Mars, the planet that might have had oceans billions of years ago, that might have harbored life, that we dream of colonizing. Jupiter, the failed star, the planet that's mostly atmosphere, with its retinue of fascinating moons. Saturn, with its magnificent rings and its moon Titan, the only moon in the solar system with a thick atmosphere. Uranus and Neptune, the ice giants, poorly explored and full of mysteries. Pluto and the Kuiper Belt, the frozen frontier, the remnants of the solar system's formation. Each one is worth visiting. Each one has something to teach us. And the travel times, long as they are just the price of admission to the greatest show in the cosmos. So when someone asks you, how long does it take to get to each planet, you can give them the numbers. 3 to 4 months to Venus, 7 months to Mars, 2 to 6 years to Jupiter, 3 to 7 years to Saturn, 8 to 13 years to Uranus, 12 to 15 years to Neptune, 9 to 10 years to Pluto. But also tell them this: it takes as long as it takes. It takes patience. It takes planning. It takes brilliant engineering and clever orbital mechanics. It takes people dedicating their careers to a single mission. It takes nations investing billions of dollars in spacecraft that won't reach their destinations for years. It takes faith that the spacecraft will work when it gets there, that the instruments will function, that the data will come back. And it takes wonder. It takes the sense of awe that comes from looking up at a distant point of light in the sky and knowing that we've been there, that we've sent our creations across the void to visit that world, to study it, to photograph it, to understand it. Space is hard. Space travel is harder. The distances are vast, the challenges enormous, the time scales long. But we do it anyway. We do it because we're explorers. We do it because we're curious. We do it because we can. And in doing it, in sending our spacecraft to every corner of the solar system, we prove something fundamental about humanity. We prove that we're not content to stay on our one small world. We prove that we have the vision to imagine distant places and the ingenuity to actually get there. We prove that we can think on timescales longer than our own lifetimes, that we can work towards goals that take decades to achieve. That's what space exploration is really about. It's not just about the science, though the science is incredible. It's not just about the images, though the images are breathtaking.
It's about pushing the boundaries of what's possible. It's about extending humanity's reach beyond Earth. It's about ensuring that our species has a future that includes more than one world. The travel times to the planets are long, but every journey begins with a single step, or in this case, a single rocket launch. And once you're on your way, once you're committed, once you're coasting through the void at tens of thousands of miles per hour, all you can do is wait. Wait and trust that everything will work. Wait and hope that the spacecraft will survive the journey. Wait and dream of what you'll discover when you get there. And when the spacecraft finally arrives, when it sends back its first images from orbit or its first data from the surface, all that waiting is worth it. Every month of travel to Venus, every year to Jupiter, every decade to Pluto, it's all worth it for that moment when we see a world up close for the first time. So here we are, humans on Earth, looking up at the sky, seeing the planets as points of light, and knowing that we've touched them. Knowing that we've sent pieces of ourselves in the form of our robots, our spacecraft, to those distant worlds. Knowing that right now, this very moment, there are spacecraft in orbit around Mars and Jupiter and Saturn. Spacecraft that are taking pictures, making measurements, gathering data. The solar system is no longer out of reach. It's not unknowable. It's not untouchable. It's ours to explore, and we are exploring it. The travel times are what they are. 3 months, 7 months, 6 years, 12 years, it doesn't matter. What matters is that we make the journey. What matters is that we send our robots to every planet and learn everything we can. What matters is that we don't stop, that we keep exploring, that we keep pushing outward. Because if there's one thing that defines humanity, it's this: we explore. We always have. From the first humans walking out of Africa to spread across the globe, to the first sailors crossing oceans, to the first astronauts leaving Earth, we explore. It's in our nature. It's who we are. And the planets? They're waiting. They've been waiting for 4.6 billion years.
They can wait a few more months or years for our spacecraft to arrive, and when we get there, when we see them up close, when we study them and photograph them and learn from them, we'll be glad we made the journey. Every planet is a world. Every world is a story. And we're just beginning to read those stories. The travel times are part of the adventure. The waiting is part of the excitement. The journey is part of the destination. So the next time you look up at the night sky and see Venus blazing in the twilight, or Mars glowing red, or Jupiter shining bright, or Saturn hanging there in the darkness, remember, we've been there. We've sent our emissaries across millions and billions of miles to visit those worlds. And we'll keep doing it, no matter how long it takes, because that's what explorers do. The solar system is our backyard. The planets are our neighbors, and we're just getting started on the greatest exploration in human history. The travel times might be long, but the rewards are infinite, because every time we visit a new world, every time we make a new discovery, we learn a little bit more about the cosmos and our place in it. And that, ultimately, is what it's all about. Understanding where we are, understanding where we came from, understanding where we're going. The planets hold those answers, and however long it takes to get there, the journey is worth it. We live in an age where we can send robots to other planets. We can land rovers on Mars. We can orbit Saturn for 13 years. We can fly past Pluto. That's not science fiction. That's reality. That's now. That's what we've achieved in just a few decades of space exploration. Imagine what we'll achieve in the next few decades. Imagine the missions we'll launch, the discoveries we'll make, the worlds we'll visit. Maybe we'll finally answer the question of whether life exists beyond Earth. Maybe we'll find it in the oceans of Europa or Enceladus. Maybe we'll find evidence of past life on Mars. Maybe we'll discover something we never expected. That's the beauty of exploration. You never know what you're going to find. Every mission has the potential to revolutionize our understanding. Every observation might be the one that changes everything. And it all starts with that first step, that first launch, that first moment when a spacecraft leaves Earth and begins its journey to another world. From that moment on, it's a matter of time and distance. The spacecraft travels day after day, week after week, month after month, year after year, covering millions and billions of miles, getting closer and closer to its destination. And we wait. We track it. We monitor it. We send it commands and receive its telemetry. We watch it traverse the solar system, this tiny piece of human technology in the vast emptiness of space. And we hope that when it reaches its destination, everything will work, that the instruments will turn on, that the cameras will take pictures, that the data will come back. And when it does, when that first image appears on our screens, when we see a distant world up close for the first time, it's magic. It's the culmination of years or decades of work by thousands of people. It's the payoff for all those months and years of travel. It's the moment when a distant point of light becomes a real place. That's what makes space exploration so incredible. We're turning lights in the sky into worlds. We're making the distant familiar. We're reaching out across the cosmic ocean and touching other shores. The travel times are long, yes, but they're not infinite. They're not impossible. They're achievable. We've proved that again and again. Every successful mission to another planet is proof that we can do this. We can cross these distances. We can reach these worlds.
And we will keep doing it, because the planets are calling.
They're out there, orbiting the sun, waiting for us. And we're coming. Maybe not as fast as we'd like, maybe not as soon as we'd hope, but we're coming. 3 months to Venus, 7 months to Mars, years to the outer planets, decades to the edge of the solar system. Those are the numbers. Those are the facts. Those are the realities of space travel with current technology. But they're also promises. Promises that with enough time, with enough patience, with enough determination, we can reach any world in the solar system. We can explore every planet, every moon, every asteroid, every comet. We can map the solar system. We can understand it. We can make it ours. Not through conquest, not through exploitation, but through knowledge, through understanding, through the simple act of being there, of seeing, of learning, of discovering. The thing about speed in space is that it's relative. Everything is moving, always. The Earth is spinning on its axis at about 1,000 miles per hour at the equator. We're orbiting the Sun at 67,000 miles per hour. The Sun itself is orbiting the center of the Milky Way galaxy at 514,000 miles per hour. And the galaxy, it's moving through space at about 1.3 million miles per hour relative to the cosmic microwave background. So when we launch a spacecraft, we're not starting from zero. We're already moving, fast. And we use that motion. Every spacecraft we launch inherits Earth's orbital velocity around the Sun. That's 67,000 miles per hour right out of the gate. Free speed, the universe's gift to space explorers. But here's the catch. That speed is in a specific direction. If you want to go to an inner planet like Mercury or Venus, you actually need to slow down to lose some of that orbital velocity so you can fall closer to the Sun. If you want to go to an outer planet, you need to speed up to climb out of the Sun's gravity well. And changing your speed in space requires fuel, lots of it.
This is why mission planning is so complex. It's not just about pointing your spacecraft at a planet and hitting the gas. It's about trajectory optimization. It's about finding the path that gets you there with the least amount of fuel, or the fastest time, or some balance between the two. It's about orbital mechanics, a field of study that's part physics, part mathematics, and part art. The Hohmann transfer orbit is the most fuel-efficient path between two circular orbits. It's named after Walter Hohmann, a German engineer who published the concept in 1925. Think about that. We figured out how to efficiently travel between planets before we'd even sent a rocket to space. The math came first. The theory came first. And decades later, when we finally had the technology to build spacecraft, we used Hohmann's equations to plot their courses. A Hohmann transfer to Mars, for example, is an elliptical orbit that touches Earth's orbit at one end and Mars' orbit at the other. You launch when Earth and Mars are positioned just right, you fire your rockets to enter the transfer orbit, and then you coast for months until you reach the other end of the ellipse, where Mars happens to be waiting for you. The timing has to be perfect. Launch a day too early or too late, and you miss. Mars is gone. You're in the wrong place, and there's no turning around, no second chances. This is why we have launch windows, specific periods of time when the alignment of planets makes a mission possible. Miss your window to Mars, and you wait 26 months for the next one. Miss your window to Jupiter, and you might wait 13 months. The planets don't care about our schedules. They move on their own timelines, set billions of years ago by the laws of gravity and motion. But Hohmann transfers aren't the only option. There are faster trajectories that require more fuel. There are slower, more efficient trajectories that take longer but use less energy. There are gravity assist trajectories that use the gravity of one planet to boost your speed toward another. The gravity assist, or gravitational slingshot, is one of the most elegant tricks in space exploration. You fly close to a planet and its gravity pulls you in, accelerating you. But you're not falling into the planet, you're falling past it, stealing a tiny bit of its orbital momentum. The planet slows down by an infinitesimally small amount, barely measurable even with our most precise instruments. And you speed up a lot. Voyager 2 used this technique to visit all 4 outer planets. It flew past Jupiter, used Jupiter's gravity to speed up and redirect towards Saturn. Then it used Saturn's gravity to redirect toward Uranus. Then Uranus's gravity to reach Neptune. Without gravity assists, a mission to all 4 outer planets would have taken decades longer, if it were even possible at all with 1970s rocket technology. The Parker Solar Probe, launched in 2018 to study the Sun up close, uses Venus for gravity assists, not to speed up, but to slow down and drop deeper into the Sun's gravity well. It's doing the opposite of what most missions do. Instead of climbing out of the gravity well, it's diving in. Each pass by Venus strips away a bit more of its orbital velocity, allowing it to fall closer to the Sun. By the end of its mission, Parker's Solar Probe will be the fastest human-made object ever, reaching speeds of 430,000 miles per hour, as it screams past the Sun at distances closer than any spacecraft has gone before. 430,000 miles per hour. That's fast enough to fly from New York to Los Angeles in less than 10 seconds. Fast enough to circle the Earth in about a minute. And yet, even at that incredible speed, even being the fastest thing humans have ever built, it still took years for Parker Solar Probe to reach its closest approaches to the Sun. Because space is big. Even the relatively small distance from Earth to the Sun, 93 million miles, takes time to traverse.
Communication delay is another fascinating aspect of these journeys. When you send a signal to a spacecraft, that signal travels at the speed of light. Nothing in the universe can go faster. Light speed is the ultimate speed limit, built into the fabric of space-time itself. And even at light speed, signals take time to travel. A signal to Mars takes between 3 and 22 minutes to arrive, depending on where Mars is in its orbit. That means when you're operating a rover on Mars, you can't drive it in real time. You can't use a joystick and steer it like a video game. By the time you see what the rover is seeing and react, it's too late. The rover has already driven off a cliff or into a rock or gotten stuck in sand. So we do something smarter. We give the rovers autonomy. We program them to analyze the terrain, to identify hazards, to make their own decisions about where to drive. We send them a list of waypoints to visit and let them figure out the safest path. We trust them to operate independently for hours at a time, while the communication delay makes real-time control impossible. At Jupiter, the communication delay is between 32 and 52 minutes one way. That's over an hour round trip. You send a command, you wait an hour, you get a response. At Saturn, it's 68 to 84 minutes one way. At Uranus, about 2.5 hours. At Neptune, over 4 hours. At Pluto, during New Horizons flyby, it was 4.5 hours one way, 9 hours round trip. Think about what that means.
The New Horizons team sent commands to the spacecraft, telling it what to do during the Pluto flyby. Then they waited 9 hours, hoping everything worked, hoping the spacecraft executed its sequence correctly, hoping nothing went wrong. Because if something did go wrong, by the time they found out about it, the flyby would be over. Pluto would be millions of miles behind the spacecraft. The mission, years in the planning, 9.5 years in flight, would have failed. And there was nothing they could do but wait and hope. That's the reality of deep space missions. You build redundancy into everything. You test and retest. You plan for every contingency you can think of. And then you launch, and you trust. You trust your engineering. You trust your math. You trust that the spacecraft will work as designed, billions of miles from home, with no possibility of repair. And remarkably, most of the time, it does work. The success rate of modern planetary missions is actually pretty high. Not perfect. We've had failures. Mars has a particularly notorious reputation for eating spacecraft. The Mars curse, they call it. Roughly half of all missions to Mars have failed. Orbiters that crashed, landers that smashed into the surface, rovers that never woke up. But we keep trying. We learn from each failure. We improve the designs. We add more testing. And gradually, we get better. The last several Mars missions have all been successful. Curiosity landed perfectly in 2012 and is still operating. InSight landed in 2018 and operated for 4 years. Perseverance landed in 2021 with the most sophisticated sky crane landing system yet devised and is currently exploring an ancient river delta. The Chinese 1011 orbiter and Zhurong rover arrived in 2021. The UAE's HOPE orbiter is studying Mars's atmosphere. We're getting good at this, really good. The technology improves with each mission. The spacecraft get more capable. The instruments get more sensitive. The autonomy gets more sophisticated. We're not just sending metal boxes to other planets anymore. We're sending sophisticated laboratories, mobile science platforms that can operate for years far from Earth. But every mission still faces the same fundamental challenge: distance. And distance takes time. There's been a lot of talk recently about new propulsion technologies that could cut travel times. Nuclear thermal rockets, for example, could potentially reduce the trip to Mars from 7 months to 3 or 4 months. That doesn't sound like much, but when you're talking about keeping humans alive in space, every month matters. Radiation exposure, muscle atrophy, bone density loss, psychological stress, these all accumulate over time. The shorter the trip, the healthier the crew arrives. Nuclear electric propulsion, using nuclear reactors to generate electricity for ion drives, could provide continuous thrust for months or years, eventually building up to much higher speeds than chemical rockets can achieve. A mission to Mars using nuclear electric propulsion might take longer initially because the acceleration is so gradual. But for missions to the outer planets, it could potentially cut years off the travel time. There's even more exotic concepts. Fusion rockets, if we can ever make them work, could provide enormous thrust with incredible efficiency. Antimatter rockets could theoretically achieve speeds approaching a significant fraction of light speed, though we currently can't produce or store antimatter in quantities larger than a few atoms. Solar sails, pushed by sunlight or lasers, could accelerate indefinitely without fuel. Project Breakthrough Starshot is a proposal to send tiny spacecraft to Alpha Centauri, the nearest star system, using powerful ground-based lasers to push ultra-lightweight solar sails up to 20% of light speed. At that velocity, the probes could reach Alpha Centauri in about 20 years. It's speculative, it's ambitious, it may never happen. But the fact that serious scientists and engineers are working on it tells you something about where space exploration might be headed.
But for now, for the missions we're actually flying, we're stuck with chemical rockets and ion drives. We're stuck with travel times measured in months and years. And you know what? That's okay, because we're doing incredible science with the technology we have. Consider what we've learned just from the Mars rovers. Spirit and Opportunity, which landed in 2004, were designed to last 90 days. Spirit lasted 6 years. Opportunity lasted 15. 15 years. In that time, Opportunity drove 28 miles across the Martian surface, studying rocks, analyzing soil, taking thousands of pictures. It found evidence of ancient water. It discovered mineral deposits that could only have formed in the presence of liquid water. It helped us understand that Mars, now cold and dry, was once a wetter, warmer world. Curiosity has been on Mars since 2012, over a decade now, and it's still going. It's climbed Mount Sharp, a 3-mile-high mountain in the center of Gale Crater, studying layers of rock that represent different epochs in Martian history. It's found organic molecules, the building blocks of life. It's measured radiation levels to help us understand what astronauts would face. It's analyzed the atmosphere, the weather, the geology. Every day, it sends back data that helps us understand Mars better. And Perseverance, the newest rover, is doing something no Mars mission has done before. It's collecting samples. Carefully selected rocks and soil that represent different geologic environments. These samples are being sealed in tubes and cached on the Martian surface. The plan is for a future mission to retrieve them and bring them back to Earth. Mars Sample Return, it's called. And if it succeeds, it'll be the first time we've brought samples from Mars to Earth. Those samples will spend years getting to Mars on the Fetch rover mission, years being collected, and then years coming back to Earth. The entire Mars Sample Return campaign might take 10 to 15 years from start to finish, a decade and a half. But those samples will be worth it, because we can do analyses in laboratories on Earth that no rover, no matter how sophisticated, can do in the field. We can use instruments that weigh tons and consume kilowatts of power. We can study the samples for years, decades even. Future scientists who haven't even been born yet will study those Martian rocks. That's the long game of space exploration. You don't get instant results. You don't get quick answers. You commit to missions that will take years to reach their destinations, years to complete their work, and years for the scientific community to fully analyze the data. It's science at the pace of orbital mechanics. And it requires a kind of thinking that's rare in modern society. We're used to instant gratification, fast food, streaming movies, same-day delivery. But space exploration doesn't work that way. You plan a mission, you build the spacecraft, you launch it, and then you wait. Years, decades sometimes. The people who proposed the Cassini mission to Saturn in the early 1980s didn't see their spacecraft launch until 1997. They didn't see it arrive at Saturn until 2004. 20 years from proposal to arrival. Some of those scientists retired before the mission ended. Some didn't live to see it. That's the timescale we're talking about. But their work lives on. The data from Cassini will be studied for generations. Every image, every measurement, every observation adds to our understanding of Saturn, of planetary science, of how solar systems work. And that knowledge is forever. There's something profound about that, about working on something that might not pay off in your lifetime, about contributing to a body of knowledge that will outlast you,
about being part of something bigger than yourself. Space exploration forces us to think long-term. It forces us to plan for the future. It forces us to invest in things we might not personally benefit from. And maybe that's one of its greatest values. Not just the scientific knowledge we gain, but the perspective it gives us. When you think about a mission that takes 12 years to reach Neptune, your priorities shift. You start thinking about what's important over years and decades, not just days and weeks. You start thinking about legacy, about what we're leaving for future generations. And the distances force us humility upon us. No matter how advanced our technology, no matter how clever our engineering, we still can't cheat physics. We still can't go faster than light. We still have to work within the constraints of orbital mechanics and propellant mass and energy budgets.
The planets are where they are, the distances are what they are, and we have to respect that. We have to be patient. We have to be persistent. We have to be willing to wait years for our spacecraft to arrive, and then wait years more for them to complete their missions. But in that patience, in that persistence, there's beauty. There's something admirable about the multi-year, multi-billion-dollar commitment to visit a planet. It says something about us as a species. It says we value knowledge. We value exploration. We value understanding our place in the cosmos. Every spacecraft we launch is a message. Not to aliens, though some of our spacecraft carry plaques and golden records with messages for potential extraterrestrial finders. No, the real message is to ourselves. It's a statement that we care about more than just our immediate needs, that we're willing to invest in understanding the universe, that we're willing to wait years for answers to our questions. The James Webb Space Telescope took nearly 30 years from initial concept to launch. 30 years. People spent their entire careers working on it. And now it's sending back images of galaxies that formed just a few 100 million years after the Big Bang. Images of exoplanet atmospheres. Images of stellar nurseries where new stars are being born. Images that are rewriting textbooks. Was it worth the wait? Ask any astronomer. Ask any astrophysicist. They'll tell you yes. Absolutely yes. 1,000 times yes. The same is true for planetary missions. Every year of travel time, every month of waiting, it's worth it for what we learn. Because these aren't just academic exercises. This is our solar system. These are our neighboring worlds. Understanding them helps us understand Earth. Understanding planetary atmospheres helps us understand climate change. Understanding planetary geology helps us understand earthquakes and volcanoes. Understanding magnetospheres helps us understand space weather and how to protect our satellites and power grids. And beyond the practical applications, there's the sheer wonder of it. The awe of seeing another world up close for the first time. The thrill of discovery. The joy of learning something new about the universe. When New Horizons sent back the first high-resolution images of Pluto, the mission team wept. Grown scientists with decades of experience, some of the smartest people in their fields, wept openly. Because they were seeing Pluto, real Pluto, not a fuzzy blob in a telescope, but a world, a place, with mountains and plains and a heart-shaped region and a thin blue atmosphere. It was real. After 9.5 years of flight, after a lifetime of wondering what Pluto looked like, they finally knew. That's the payoff. That's what makes the long journey times worthwhile. The moment of discovery. The moment when a distant point of light becomes a world. And we're just getting started. There are so many places we haven't been yet. We've never orbited Uranus or Neptune.
We've never sent a probe into Neptune's atmosphere. We've never landed on Titan's methane lakes. We've never explored Europa's subsurface ocean. We've never studied Enceladus's geysers up close. We've never visited most of the solar system's smaller bodies, the asteroids and comets and Kuiper Belt objects. Each one of those missions will take years. Each one will require patience. Each one will push the boundaries of our technology and our endurance. But we'll do them because that's who we are. Explorers, curious, ambitious, willing to wait years for answers to our questions. The travel times to the planets aren't obstacles. They're part of the adventure. They're the price of admission to the greatest exploration in human history. And we're paying that price gladly, because what we get in return, the knowledge, the discovery, the understanding, is priceless. So yes, it takes months to reach Venus and Mars, years to reach the gas giants, over a decade to reach the ice giants and Pluto. Those are the numbers, those are the facts. But they're also invitations. Invitations to think bigger, to plan longer, to dream further, to imagine what we might discover on those distant worlds, to wonder what secrets they hold, to hope that maybe, just maybe, we'll find answers to questions we haven't even thought to ask yet.
The journey is long, but the destination is worth it, always. Let's talk about something we haven't discussed yet. What these travel times mean for humans, not robots. Us. Real people with real bodies that need food, water, air, and something approaching normal gravity to stay healthy. Because here's the thing. We can send a robot to Mars and wait 7 months. The robot doesn't care. It doesn't get bored. It doesn't need entertainment. It doesn't suffer from cosmic radiation. It doesn't lose bone density or muscle mass in microgravity. It just sits there, dormant or performing minor tasks, waiting to arrive. Humans? We're complicated. We're fragile. We're demanding. We need about 2,000 calories a day. We need water. We need oxygen. We generate waste. We get sick. We get depressed. We need social interaction. We need something to do. 7 months is a long time to keep a human alive and sane in a metal can hurtling through the void. The International Space Station has taught us a lot about long-duration spaceflight. Astronauts regularly spend 6 months aboard the ISS. Some have stayed nearly a year. Scott Kelly spent 340 consecutive days in space. Russian cosmonaut Valery Polyakov holds the record at 437 days. That's over 14 months. 14 months in microgravity. And they paid for it. Scott Kelly came back 2 inches taller because his spine stretched out without gravity compressing it. His vision was affected. His bone density decreased despite rigorous daily exercise. His cardiovascular system changed. His gene expression actually altered. His telomeres, the protective caps on chromosomes, lengthened in space and then shortened rapidly upon return to Earth, potentially accelerating aging. And that's in low Earth orbit, just 250 miles up. That's still inside Earth's magnetosphere, which provides some protection from cosmic radiation. On a trip to Mars, you're outside that protection. You're exposed to galactic cosmic rays, high-energy particles from distant supernovae. You're exposed to solar particle events when the sun occasionally hurls massive amounts of radiation into space. A big solar event during a Mars transit could be lethal. Current spacecraft designs for human Mars missions include water walls or polyethylene shielding to reduce radiation exposure. But you can't eliminate it. The astronauts going to Mars will receive more radiation than any human has ever been exposed to. We don't fully know what that will do to them long term. We can estimate based on nuclear accident survivors and cancer patients who received radiation therapy, but it's not the same. It's a different type of radiation, delivered over months instead of hours or days. And then there's the psychological challenge. 7 months in a spacecraft with the same small group of people. No privacy, no escape, no ability to go outside and feel wind on your face or see a natural horizon. The Earth getting smaller and smaller behind you until it's just another star. Mars ahead of you, still just a point of light for most of the journey, growing slowly, so slowly, into a disk. NASA and other space agencies study this. They run simulations where volunteers spend months in isolation in Mars analog habitats. They study Antarctic research stations, where crews spend long winters cut off from the rest of the world. They study submarines, where sailors spend months underwater in confined spaces. They're trying to understand how to select crews who can handle it, how to design habitats that minimize psychological stress, how to structure the days to maintain mental health.
Because the journey to Mars is just the beginning. Once you get there, you're staying for a while. The planets align for efficient Earth-to-Mars transfers every 26 months. If you go to Mars, you're staying at least 18 months before the return window opens. 18 months on Mars, plus 7 months to get there, plus 7 months to get back. That's 32 months, nearly 3 years. 3 years away from Earth. 3 years where if something goes wrong, there's no rescue coming. You're on your own. This is why every proposed human Mars mission is so expensive. You're not just building a spacecraft, you're building a mobile habitat that can keep humans alive for 3 years. You need redundant life support systems. You need spare parts for everything. You need food for 3 years that won't spoil. You need water recycling that approaches 100% efficiency. You need psychological support systems. You need medical equipment and supplies for any conceivable emergency. You need power systems that will work reliably for 3 years. You need communication systems that can maintain contact with Earth despite the vast distances and communication delays. And the cost? Estimates vary, but we're talking hundreds of billions of dollars for the first human Mars mission. Maybe $500 billion when you add up all the development costs, the spacecraft, the surface habitat, the supplies, the training, the ground support. That's more than the entire Apollo program adjusted for inflation. Is it worth it? That's the question that's been debated for decades. Some say yes, absolutely. Human exploration is fundamentally different from robotic exploration. Humans can make observations and decisions in real time. Humans can adapt to unexpected situations. Humans can take risks that we'd never program into a robot. And there's the inspirational value, the symbolism of humans setting foot on another planet. Others say no. Robots can do the science cheaper and safer. Why risk human lives when rovers and landers and orbiters can gather the data we need? Why spend hundreds of billions of dollars on a flags and footprints mission when that same money could fund dozens of robotic missions to Mars, Europa, Titan, Enceladus, and beyond? Both sides have valid points, and the debate continues. But here's what's interesting. The travel times themselves might be a deciding factor. 7 months in space is manageable,
barely with current technology. Uncomfortable, risky, but possible. But what about Jupiter? Jupiter's moons, Europa and Ganymede and Callisto, are some of the most scientifically interesting places in the solar system. If we ever want to send humans there, we're talking about 2 to 6 years just to get there. Years spent on the moons, and then years to get back. That could be a decade-long mission, maybe longer. Can we keep humans alive and sane for a decade in space? With current technology, probably not. The radiation exposure alone would be catastrophic. The bone density loss would be severe. The psychological toll would be immense. So for human exploration, the travel times act as a natural boundary. Mars is at the edge of what's possible. Maybe we could push to the asteroid belt, but the outer planets, those are robot territory. At least for now. At least until we develop better propulsion, better radiation shielding, better life support, maybe even artificial gravity systems. There's another factor we haven't discussed: cost per day. Every day a spacecraft is in transit is a day you're paying mission control staff, a day you're paying for deep space network time to track and communicate with the spacecraft, a day the spacecraft's components are aging, getting closer to failure, a day of risk. For robotic missions, this cost is manageable. A spacecraft costs what it costs to build, and then the operational costs during the mission are relatively small compared to the development costs. Millions per year instead of billions. But for human missions, every day is expensive. You're consuming supplies, you're using power, you're putting wear and tear on life support systems, you're exposing the crew to radiation. The longer the mission, the higher the cost and risk. This is why there's so much interest in faster propulsion systems. Not just because faster is cool, but because faster is safer and cheaper for human missions. Cut the Mars transit time from 7 months to 3 months, and you've significantly reduced the radiation exposure, the supply requirements, the psychological strain. You've made the mission more feasible.
Nuclear thermal propulsion could do this. A nuclear reactor heats hydrogen propellant to extreme temperatures, producing thrust. It's more efficient than chemical rockets and can provide higher speeds. NASA has tested nuclear rocket engines in the past, back in the 1960s and 70s. The NERVA program demonstrated that nuclear thermal rockets could work. Then the program was canceled due to budget cuts and changing priorities. Now there's renewed interest. NASA is working on nuclear thermal propulsion again. They're partnering with DARPA on a demonstration mission called Draco that could fly in the late 2020s. If successful, it could pave the way for nuclear rockets on Mars missions. Nuclear electric propulsion is another option. Instead of using the reactor's heat directly for thrust, you use it to generate electricity, which powers ion drives. Ion drives provide very low thrust, but they can run continuously for months or years, gradually building up enormous speeds. The Dawn mission used solar-powered ion drives to visit Vesta and Ceres. A nuclear-powered version could venture much farther, much faster. But even with these advanced propulsion systems, we're still talking about months to reach Mars, years to reach the outer planets. We're not going to get Star Trek-style travel where you zip across the solar system in hours or days. The distances are too vast. The physics won't allow it. Unless we develop something truly revolutionary. Fusion propulsion, matter-antimatter annihilation, even more speculative concepts like space-time manipulation. These are the dreams, the far future possibilities, the technologies that,
if they're possible at all, might one day make the solar system feel small. But for now, for the foreseeable future, we work with what we have: chemical rockets, ion drives, maybe nuclear thermal propulsion, if we're lucky. And we accept the travel times those technologies impose. There's a historical parallel here. When European explorers set out to circumnavigate the globe in the 15th and 16th centuries, their journeys took years. Magellan's expedition took 3 years to sail around the world. 3 years of danger, hardship, starvation, disease. Of the 270 men who started the journey, only 18 made it back. Magellan himself was killed in the Philippines. But they did it. They proved it was possible. They mapped the world. They opened trade routes. They changed history. Later expeditions were faster, safer, more successful as the technology improved. By the 19th century, steamships could circle the globe in months instead of years. By the 20th century, airplanes could do it in days. Now you can fly around the world in about 40 hours if you really want to. Space exploration is following a similar trajectory. Our first missions were crude, dangerous, barely successful. But we're getting better. Each decade, our spacecraft are more capable, more reliable, more sophisticated. The travel times aren't decreasing much, not yet. But our ability to do science during those long journeys is improving dramatically. And maybe that's okay. Maybe the journey times are fixed, at least for now, but what we can accomplish during those journeys continues to expand. Think about it this way. Voyager 2 flew past Uranus and Neptune in the 1980s. Brief flybys, a few hours of close observations. The images were fuzzy by modern standards. The instruments were primitive compared to what we have now.
If we sent a mission to Uranus or Neptune today, it would have high-resolution cameras, sophisticated spectrometers, radar systems, magnetometers, particle detectors. It would have computers thousands of times more powerful than Voyager's. It would have communication systems that could send back data at much higher rates. It would have autonomy systems that could respond to unexpected discoveries without waiting hours for instructions from Earth. The journey would still take 12 to 15 years, but the science return would be exponentially greater. So in a sense, the travel time is becoming less of a limitation. Yes, it still takes years to get there, but we're making better use of those years, both during the journey and after arrival. And there's something else, something we haven't really grappled with as a society. These long mission timelines change the nature of the work. They require institutional stability. They require long-term funding commitments. They require trust that the mission plan today will still be supported a decade from now. That's not easy, especially in democracies where administrations change every 4 or 8 years. A mission proposed by one president might be canceled by the next. A mission funded by one Congress might have its budget cut by the next. There's no guarantee. The James Webb Space Telescope survived multiple attempts to cancel it. It was over budget, behind schedule, politically unpopular in some quarters. But enough people believed in it, fought for it, kept it alive through multiple administrations and congressional sessions, and now it's revolutionizing astronomy. The same is true for many planetary missions. They survive because there are people,
Career scientists and engineers and administrators who believe in them and advocate for them even when the political winds shift. They survive because the scientific community rallies behind them. They survive because enough of the public cares about space exploration to make it politically risky to cancel missions. This is the hidden challenge of long-duration space missions. Not the engineering, though that's hard. Not the physics, though that's unforgiving. But the politics, the funding, the institutional will to see a mission through from conception to completion over decades. And yet we do it. Somehow, despite all the challenges, despite the long timelines, despite the political complications, we keep exploring. We keep launching missions. We keep sending our robots to distant worlds. Why? Because the questions are too compelling to ignore. Is there life on Europa? What's beneath Titan's lakes? What happened to Mars's atmosphere? How did giant planets form? What are the Kuiper Belt objects made of? These questions demand answers, and the only way to get those answers is to go there, to send our spacecraft on those long journeys and wait patiently for them to arrive. There's a concept in science called delayed gratification, the ability to resist immediate rewards in favor of larger rewards later. It's considered a mark of maturity, of intelligence, of civilization. And space exploration is the ultimate expression of delayed gratification. We invest billions of dollars today for knowledge we won't receive for years or decades. We plant trees under whose shade we may never sit. But future generations will sit under that shade. They'll study the data from our missions. They'll build on our discoveries. They'll ask new questions prompted by our answers. And they'll launch their own missions on journeys that we can barely imagine.
The solar system is our first step. The travel times to the planets are our training wheels. We're learning patience. We're learning to think long-term. We're learning to commit to goals that outlast any individual's career or lifetime. And when we finally do venture beyond the solar system, when we send missions to other stars, the travel times won't be measured in years, but in decades or centuries. The Voyager spacecraft, now in interstellar space, will take 40,000 years to reach the distance of the nearest star if they were headed that way. 40,000 years. That's longer than all of recorded human history. But maybe someday we'll build spacecraft that can make that journey faster, maybe in decades instead of millennia. And the lessons we're learning now, sending missions to Mars and Jupiter and Neptune, will be the foundation for those future missions. Every spacecraft we launch, every mission we complete, is a proof of concept. Proof that we can plan long-term. Proof that we can build things that work billions of miles from home. Proof that we can be patient. Proof that we can dream big and then make those dreams real. The planets are waiting. They've been waiting for billions of years. They can wait a few more months or years for our spacecraft to arrive. And when they do arrive, when we finally see those worlds up close, when we analyze their atmospheres and study their geology and search for signs of life, it will all be worth it. Every month of travel, every year of waiting, every decade of planning and preparation, all worth it. Because in the end, space exploration isn't really about the destinations. It's about the journey. Not the physical journey of the spacecraft, though that's part of it, but the journey of humanity. Our journey from a species bound to one world to a species that explores the cosmos. Our journey from looking up at the stars and wondering to actually going there and finding out. The travel times to the planets are just numbers. 3 months, 7 months, 12 years. They're constraints we work within, challenges we overcome, facts we accept. But they're also opportunities. Opportunities to test our patience, to prove our commitment, to demonstrate that we can think beyond our own immediate needs and invest in knowledge for its own sake. So when you look up at the night sky and see Venus or Mars or Jupiter shining down at you, remember, we've been there. We sent our machines across millions and billions of miles to visit those worlds. And yes, it took months or years for them to arrive, but they got there. We did that. Humanity did that. And we're not stopping. Right now, there are spacecraft in flight to multiple destinations. The Psyche mission is heading to a metal asteroid. The Europa Clipper is on its way to Jupiter. Future missions are being planned to Uranus, to Enceladus, to Titan, to Triton, to dozens of other worlds. Each one will take years to arrive. Each one will require patience and funding and hope. Each one could fail. Each one could succeed. Each one will teach us something new about the solar system and our place in it. The journey continues. The exploration never stops. And the travel times, long as they are just the price we pay for answers to the biggest questions we can ask. How did we get here? Where did the solar system come from? Is there life beyond Earth? What makes a planet habitable? What can other worlds teach us about our own? These questions are worth waiting for. They're worth every month of travel time, every year of mission operations, every decade of planning and preparation. Because in the end, we're not just exploring the solar system, we're exploring ourselves, our capabilities, our curiosity, our capacity for wonder, our ability to work together toward goals that transcend borders and politics and individual lifetimes. Space exploration is humanity at its best. Patient, curious, ambitious, cooperative, visionary. And the long travel times to the planets don't diminish that. They enhance it. They make the achievement greater. They make the discoveries more precious. They make the whole endeavor more profoundly human. So yes, it takes months to reach Mars and years to reach Neptune. But every single one of those months and years is part of the greatest adventure in human history. The adventure of leaving our cradle world and reaching out to touch the cosmos. The adventure of transforming from planet-bound to spacefaring. The adventure of becoming the kind of species that doesn't just wonder about distant worlds, but actually goes there and finds out. That's what the travel times represent. Not obstacles, not problems to be solved, but proof. Proof that we're doing something hard, something worthwhile, something that matters. The planets are out there, orbiting the sun, just as they have for billions of years. And now, for the first time in all that vast span of time, they have visitors. Us, our robots, our spacecraft, our curiosity made manifest in metal and circuits and cameras. 3 months to Venus, 7 months to Mars, years to the outer planets. These are the numbers. These are the facts. These are the realities of exploring the solar system in the 21st century. And they're beautiful. Every single one of them. Because they mean we're doing it. We're actually doing it. We're exploring our cosmic neighborhood. We're visiting other worlds. We're becoming the spacefaring species we always dreamed of being.
The journey is long, but we're on our way. And that, ultimately, is what matters most.